Okay, welcome back to channel. In last video we have started our new chapter, reciprocating air compressor. We have seen what is meant by compressor, what is meant by reciprocating compressor, its classifications, and some terms which are related to reciprocating air compressor. In this video we will discuss about working of reciprocating air compressor. Let's check first this diagram. Before going to start PV diagram, pressure velocity diagram, let's check its working. Consider our piston is at top dead center and moving downwards. Then when it starts, initially outlet pressure and inlet pressure are same. Okay. When inlet pressure decreases slightly below of atmospheric pressure, air will start moving in of cylinder. That is when piston at TDC starts moving towards bottom dead center, air enters from atmosphere to inside. Okay. Now let's say suppose piston is at some intermediate position and moving downwards, air is coming inside. Then as air is coming inside, quantity of air is inside increasing. So with increasing volume there will be no any decrease in pressure because air is occupying that space and pressure inside is maintained constant. Now when piston is at BDC, then all the cylinder is filled up of air at constant pressure. It is from the pressure at which air enters is constant throughout this process from moving piston from TDC to BDC. Pressure remains constant or air enters at constant pressure. Then next piston, now after this piston will start move from BDC to TDC. Now consider at start, initially pressure is low pressure, your spring delivery valve is loaded with spring, so it will not open initially. Now consider piston is moving towards TDC, so when piston starts to move in upward direction, your suction valve or entry valve closes delivery valve as inside pressure is just start to build up and it is not sufficient to open delivery valve, so delivery valve is also closed, so all the air inside here gets compressed. Now at some intermediate position or point, inside pressure is just above delivery pressure. At that point delivery valve opens and air starts move towards reservoir or tank at a constant pressure. When our piston is moving at TDC, delivery valve is still open and all air present here is delivering to reservoir and again constant pressure. That means from some intermediate position at which air pressure is above delivery pressure, slightly above delivery pressure, from this point to TDC pressure is maintained constant again. So compression is actually taking place only from position of BDC to some intermediate position. Afterwards pressure is remains constant. So let's look this on PV diagram. So there are two derivations in mentioned syllabus. First is without considering clearance volume, that means we are considering our TDC at cylinder head. Okay. Now during first movement when piston moves from TDC to BDC, we are adding air, so volume is increasing but at constant pressure, so we get horizontal line or constant pressure process. Then from 1 to 2, when piston starts moving towards TDC, pressure will start to build up. Okay, let's say it is according to any polytropic process, and for that we can write this can be shown by P raised to n is equal to constant. N is polytropic index. After some intermediate position, when pressure is slightly above delivery pressure, then air will deliver at constant pressure when piston is moved towards top dead center. Then all air is delivered, then again pressure reduces to inside pressure reduces to atmospheric pressure, again suction, compression, delivery. So these cycles repeat continuously. Okay, now we want to calculate work done. We know that in case of PV diagram, area under curve represents work done. That means we have to calculate, find out what is this total area. Okay, now this area can be viewed as, this total pressure is P2, this is P1, this total length is V1, this total length is V2. So this required area can be viewed as this total area, it is this A1, plus this total area considering this curve 2 which is under polytropic process, minus this area is A3. Here this is rectangle, this is rectangle, and this is some curve. So here height is P2, volume is V2, so this area will be P2 V2 here. Here P1 is height, V1 is the volume or length, so here this area will be P1 V1. For this polytropic process, we know for polytropic process work done is given by P2 V2 minus P1 V1 upon n minus 1. So at the same term we will get this P2 V2 minus P1 V1 plus P2 V2 minus P1 V1 upon n minus 1. Then by arranging term we will get n upon n minus 1 P2 V2 minus P1 V1. Now take common P1 V1 outside, we will get this equation P2 V2 upon P1 minus P1 V1 minus 1. Now this compression is according to process polytropic process PV raised to n, and for that we can write P2 V2 raised to n is equal to P1 V1 raised to n. Then we want to replace this V2 by V1 in terms of pressure ratio. So at the same terms P2 by P1 is equal to V1 by V2 raised to n. Here this is V2 by V1, so at this thing for V2 by V1 this plus becomes minus here. Then for V2 by V1 it becomes P2 by P1 raised to minus 1 upon n. So putting this value in this equation, we will get work done is equal to n upon n minus 1 P1 V1 into bracket P2 by P1 into P2 by P1 raised to minus 1 upon n minus 1. So this comes to this equation. Okay, this comes to our this equation. This is nothing but work done by compressor in polytropic compression. This compression is according to polytropic process. Okay, then this work done is per stroke. We have considered one stroke only, so this compression is per stroke, and it is denoted by W polytropic is equal to n upon n minus 1 P1 V1. This is the volume handled in stroke. This is the remaining part. We also know that PV is equal to MRT. Then work done formula changes to n upon n minus 1 P MRT1 into bracket P2 by P1 raised to n minus 1 upon n minus 1, where m is the mass handled by compressor in one stroke. Remember this formula is per stroke. Okay, now here we are assuming polytropic compression. Then instead of polytropic, if adiabatic compression is there, then this polytropic index will changes to adiabatic. Here if this compression is according to polytropic adiabatic compression, then work done in adiabatic process is equal to, instead of n we will use gamma here, gamma upon gamma minus 1 P1 V1 into bracket P2 by P1 raised to gamma minus 1 upon gamma minus 1. Now we will consider another case, that is if compression is according to isothermal process, then starting from area relations we get work done is equal to A1 plus A2 minus A3. Okay, we have calculated A1 as P2 V2, A3 is minus P1 V1. Then as process is isothermal, we know that for isothermal process work done is given by P1 V1 log to the base C P2 by P1. Again here P2 V2 comes to be P1 V1 because process is isothermal between 1 and 2, so we can cancel out each other. Then work done in isothermal compression per stroke is equal to P1 V1 log to the base C P2 by P1. So this is the work done per stroke. Now what is the power consumed by compressor? That is nothing but indicated power. So indicated power is work done per second, so is equal to work done per stroke into number of strokes per minute, okay, per second, sorry, number of strokes per second. Okay, then for single acting we know that when there is one stroke there is only one compression, and if there are n strokes there will be n cycles, so n compression cycles. So indicated power is polytropic work into n upon 60. Okay, then for double acting we know that when there are n strokes then there will be 2n number of compression cycles, so indicated power is 2n upon 60. Okay, n is rpm of compressor. Now in sometimes in problems they are directly given mass flow rate or volume flow rate directly, so in that case we don't require to convert, or we don't want to consider this rpm. We can directly calculate it indicated power as n upon n minus 1 p1 v1 dot v1 that is volume flow rate to pt by p1 is n minus 1 upon n minus 1, or instead of p1 you can use m dot in case of mrt1 relation. Okay, this is for indicated power. Then next is efficiency. In case of compressor, as you know, compressor requires shaft power or mechanical energy is supplied by electrical motor, and electrical motor requires electrical power to run. Then first we will define electrical efficiency. It is a ratio of shaft power to electrical power. Okay, then second is mechanical efficiency. It is a ratio of indicated power to shaft power. Then last one is the overall efficiency. It is a ratio of indicated power and initial input is electrical power. It is product of electrical efficiency into mechanical efficiency. So this is for efficiencies and work done. Next video we will discuss about work done with considering clearance volume and what are its effect, and we will define new efficiency, that is volumetric efficiency. If you like this video, please comment, like and share. Thank you.